Hello everybody, welcome to Chapter 3 of Introduction to Atmospheric Dynamics. This chapter tackles applications of the basic equations of motion that we've derived in the previous two chapters, and in particular we're going to start with the topic of gradient wind balance, which actually turns out to be pretty important for a bunch of different atmospheric phenomenon that affect our everyday lives. So in order to actually tackle this idea of gradient wind balance, we're going to need to actually define a new coordinate system. So we talked previously a little bit about vertical coordinates and when one would choose, for instance, pressure coordinates in the vertical versus height coordinates. But this defines a new horizontal coordinate system. Now you're probably wondering, why are we actually using another coordinate system, or why do we have to define a new coordinate system? Well, the goal here is that these coordinates hopefully help us simplify the equations of motion and give us a more intuitive look at what exactly these equations are describing. For something like the very generic horizontal wind equations, it can be very difficult in order to untangle how exactly fluid parcels are moving around in response to the various forces that they're experiencing. And so with natural coordinates, we're going to actually be able to reduce those three horizontal equations of motion to a single equation of motion that we can then analyze in the context of balanced flow. So we know that at large scales the atmosphere is in this state of balance, and in general for flows that are in geostrophic balance, as discussed in Chapter 2, we know that you have, for instance, pressure gradient force being balanced by Coriolis force, leading to fluid parcels that follow along lines of constant geopotential. And so this idea of balance between forces allows us to infer various ideas about how exactly fluid parcels are moving around in this environment, and we can use this information then in order to understand how force balance then gives rise to larger scale behaviors in fluid motion. So just to recall, geostrophic balance again is this balance between Coriolis and pressure gradient force. So in this case we have a pressure gradient force which is directed northward. The purple lines in this diagram here are indicative of lines of constant pressure with high pressure to the south and low pressure to the north. In correspondence with how the pressure gradient force behaves, recall that it always forces air parcels to move from regions of high pressure to regions of low pressure. The Coriolis force, on the other hand, is it's a force that is induced on fluid parcels as a result of their motion in a rotating coordinate system. So the fact that the planet itself is rotating gives rise to this Coriolis force, which is then directed to the right of the fluid parcel's direction of motion in the northern hemisphere. So in this case we have a fluid parcel initially at rest. It experiences a pressure gradient force. Here we're at the left hand side of the diagram. That pressure gradient force induces a northward velocity in the fluid parcel in the direction of the green arrows. As that fluid parcel then accelerates, Coriolis force is then able to induce an additional force to the right of the direction of motion. And as a consequence, the fluid parcel ends up turning to the right. This Coriolis force continues to intensify and alter the direction of the fluid parcel until the fluid parcel ends up moving in such a manner that force is perfectly balanced between pressure gradient force directed northwards and Coriolis force directed southwards. Hence, under geostrophic balance, we observe that these fluid parcels will be moving along lines of constant pressure. And in particular, they're moving in such a way that low pressure is to the left of the direction of fluid motion and high pressure is to the right. Pressure gradient force being directed to the left and Coriolis force being equal and opposite in the southern direction. In real life, of course, we don't have these very pretty pictures of perfect linear flow with lines of constant pressure that are perfectly aligned with lines of constant latitude, for instance. And so we ended up in this environment where for the most part you have that fluid parcels are largely behaving in correspondence with the geostrophic balance. That is, we have fluid parcels which are moving in the direction of lines of constant pressure, but we also have curvature associated with the flow, and that presence of curvature actually ends up distorting the flow and distorting the balance that individual fluid parcels are experiencing. Here we are looking at a plot of wind barbs observed in the upper troposphere, so at an altitude of about 300 millibars. Here the black lines are indicative of lines of constant geopotential. Recall we discussed how this is kind of analogous to lines of constant pressure in a height coordinate system, and so you will have that fluid parcels will tend to move along lines of constant geopotential. The wind barbs here are indicative of the overall wind strength. Now, the geostrophic flow is shown here with the blue wind barbs, and the observed wind is shown here with the red wind barbs. You'll notice that in a few places that, for the most part, although there's largely correspondence, I would say, between the geostrophic and observed wind flow, you don't observe perfect correspondence in every location. However, let's concentrate for a moment on the geostrophic flow here. Again, you'll notice that the wind barbs are pointing in long lines of constant geopotential here. And one other thing I want to emphasize for the geostrophic wind is the fact that the strength of the geostrophic wind here is going to be proportional to or inversely proportional to the distance between lines of constant geopotential. That is, in regions where lines of constant geopotential are farther apart, you actually have slower wind motion, and in regions where they're closer together, you have faster wind motion. So in particular, you'll notice, for instance, here where there's very sharp curvature associated with the flow and bunching of these lines of constant geopotential, you observe very fast wind speeds associated with the wind barbs. And in regions, for instance, on the western side of this diagram, where you have larger distance between lines of constant geopotential, you have much slower motion associated with individual fluid parcels. There are a few other things to note here that we'll touch on later. One is that the observed wind speeds do not correspond exactly with the geostrophic wind speeds. You'll notice, for instance, in the regions where the curvature is strongest, that the geostrophic wind speed here in this diagram actually overestimates the overall wind speed. And in regions where the curvature is weaker, or where you basically have clockwise motion associated with the flow, in those regions you observe that the observed wind speed is slightly faster than the geostrophic wind. And so this whole idea of gradient wind balance that we're going to touch on in this lecture will actually allow us to explain why we observe this discrepancy between our geostrophic balance approximation and the observed wind flow. Okay, so this basically just summarizes what I talked about. At these upper levels, again, we have friction is negligible, and so the observed wind is largely observed to be parallel to geopotential height contours on a constant pressure surface, and wind is faster when height contours are close together, and wind is slower when height contours are farther apart. We're going to talk about this in the context then of the equations of motion, why this might be the case. Here we have an idealized diagram then showing basically south to north and west to east, and we have geopotential contours which are depicted here. Again, this is basically just a toy figure in order to discuss these concepts associated with geopotential. Okay, so we have geopotential that increases to the south in accordance with what we would expect for higher temperatures farther to the south, the pushing up those geopotential contours, and so the pressure gradient force in this diagram will be directed to the north from higher geopotential to lower geopotential. Here we're going to define a distance delta y, which represents the distance between phi naught and phi naught plus 2 delta phi. That is basically crossing two geopotential height contours, and we're going to estimate then the geostrophic balance that's experienced by a wind parcel moving along phi naught plus delta phi. So this technique is known as a finite differences technique. Basically, we're going to be approximating a derivative in the meridional direction, that is in the north-south direction, with a difference of two quantities. This is kind of analogous to how one, for instance, would go about studying calculus for the first time, saying that a gradient is proportional to a slope, and so our slope here is simply going to be rise over run, and the run here is delta y. So the difference in geopotential height between these two locations, that is the rise of the field between these 2 points, is given by delta phi, which is phi naught minus phi naught plus 2 delta phi. That is basically just the geopotential height difference between these two contours. And if you take the difference between those two, again remembering that since this is a meridional difference, we're doing north minus south, so we're doing the smaller geopotential height contour minus the larger geopotential height contour. We have a geopotential height difference of -2 delta phi over this distance. So using this finite difference approximation, then we would say that the meridional derivative of the geopotential height between these 2 points then is approximately equal to -2 delta phi over delta y. Okay, so from the horizontal momentum equations, that is the very basic equations of motion that we discussed in Chapter 1 of this course, we have that the fluid evolves, that is basically the velocity of the flow evolves largely in accordance with the Coriolis force and pressure gradient force terms. If we expand this in component form, we have an evolution equation for the horizontal momentum and one for the zonal momentum and another one for the meridional momentum. So the meridional gradient of the geopotential that we just calculated actually appears here as the second term in this meridional velocity equation. That is, it then determines how the meridional velocity changes. Again, this makes sense because the geopotential height difference in the meridional direction is inducing a pressure gradient force on the fluid parcel and consequently is pushing it in the northward direction. If we consider the geostrophic approximation, that is, if we consider flow in balance where the velocity field is unchanging, then we arise at an equation where Coriolis force is exactly balanced by the pressure gradient force. And so we can actually calculate the geostrophic wind speed. Here we can actually calculate the zonal geostrophic wind speed, U sub g, from the Coriolis force term, and using the finite difference representation of the geopotential height term. So using this force balance under geostrophic approximation, we have negative FUG is approximately equal to -2 delta phi over delta y. And so along this height contour, phi naught plus delta phi, we actually have that the velocity of a fluid parcel located at that point will have a zonal velocity approximately given by twice this delta phi over delta y distance. If we now take this delta y distance and we translate it over to the right-hand side of the diagram where we have a larger spacing between geopotential height contours. Now, notably here, these red lines, that is the delta y distance, is the same on the left-hand side of the diagram as it is on the right-hand side of the diagram. But on the right-hand side of the diagram, the distance between geopotential height contours is simply delta phi and not 2 delta phi. So what that implies from geostrophic balance is that on the left-hand side of the diagram where you have closer bunching of these geopotential height contours, we actually have a larger zonal wind speed. So on the left-hand side, we have that the zonal wind speed is proportional to 2 delta phi. Whereas on the right-hand side, because over the same meridional distance, we only have a geopotential height change of delta phi, we have that the zonal wind speed is approximately half that on the left-hand side of the diagram. So namely, if you have twice as much bunching of geopotential height contours, then you have twice as much zonal velocity predicted from the geostrophic wind. All right, so just to emphasize kind of what's going on here in the connection with the temperature gradient, again, recall that geopotential height contours tend to increase in accordance with in accordance with layer thickness, which is proportional to temperature. So, in other words, warmer temperatures are associated with larger volumes, And those larger volumes of air then push up the geopotential in these regions, and so you end up with higher geopotential contours along the same pressure surface in warmer regions. So consequently, you can use this actually to connect the geostrophic wind speed with the temperature gradient as well in the flow. All right, so just to review what we've done then, we've estimated the derivatives of the geostrophic balance relationship using finite differences. This finite difference relationship then allows us to estimate the magnitude of the flow, and it allows us to conclude that if you have more bunching of geopotential height contours, then you will also have a stronger geostrophic wind. In this case, there's also consistency with what we would expect from the equations of motion. The direction comes out correctly. That is, we have that the geostrophic flow is going to be directed to the east when the pressure gradient force is directed to the north, and that the strength of the wind is proportional to the strength of the gradient experienced by the fluid parcel. So in the case of the observed wind, again, flow tends to be along lines of constant geopotential, but this presence of curvature actually complicates things a little bit. Recall that in our derivation a moment ago, although in our toy diagram we did show curvature in the plot, it was neglected in our calculation because of the fact that we eliminated that term associated with transport of the horizontal momentum. That is, in our simplification that we used, we assumed geostrophic balance, and geostrophic balance again is simply a balance between pressure gradient force and Coriolis force. There is no curvature associated with the flow that is included in this calculation. There's one thing to emphasize here is that this term curvature tends to be overloaded a lot in the atmospheric sciences. Specifically, it's overloaded between two concepts, one of which we already discussed earlier, and that is the curvature of the planet itself. The curvature that I'm talking about here is actually curvature of geopotential height contours. So that would even be the case in, for instance, a flat two-dimensional map. You have curvature associated with these geopotential height contours, and you have flow which is moving along curves. You can imagine, for instance, fluid parcels moving around a tropical cyclone. They have a curvature associated with them as they move around that tropical cyclone. This is not to be confused with the curvature of the planet, which plays a different role in the evolution of the flow and gives rise to the Coriolis force that is experienced by the fluid parcel. The curvature that we're talking about here is a local curvature associated with bending of geopotential height contours. So that curvature that I'm discussing, again, shows up in this upper tropospheric diagram at 300 millibars. We see curvature associated with those lines of constant geopotential here as they curve around a local low-pressure system located in the top middle of the diagram. Okay, so where is the curvature in these equations then? So again, the geostrophic balance relationship, which simply describes balance between pressure gradient force and Coriolis force, does not include curvature associated with the flow. It basically assumes that you have a local balance between pressure gradient and Coriolis force and neglects curvature from that calculation. So we need to actually include curvature in our diagnostic equations in order to understand how wind speeds would then be affected by the curvature of the underlying flow. So that is where our motivation then comes in for these natural coordinates. Natural coordinates arguably give one of the simplest ways in which we can incorporate curvature in the flow. This will allow us to then develop a new balance relationship, a new diagnostic balance that then exists between pressure, gradient force, Coriolis, and curvature, and allow us to explain why there is this discrepancy between the observed wind speeds and the geostrophic wind speeds. Okay, so the way that these natural coordinates are going to be formulated is to use basically direction vectors. Again, coordinates, especially horizontal coordinates, basically rely on you defining two primary directions. Recall, in the case of the regular latitude-longitude coordinate system, you have a northward coordinate vector and you have a eastward coordinate vector. Those define the basis vectors then for the regular latitude-longitude coordinate system. Any two basis vectors, as long as they're not aligned with each other, can actually be used to define a coordinate system. Given these two basis vectors, you can then write any point on the grid as a combination of those two vectors, namely as a combination of movement in one direction plus movement in another direction. So this gives us a lot of freedom in how we actually choose our coordinates, and in particular we can choose coordinates that change, that is, we can choose these basis vectors that change depending on where you are in the flow. And more importantly, we can actually choose basis vectors that change in accordance with the behavior of the local fluid flow. This is going to be key in our definition of these natural coordinate vectors. Okay, so natural coordinates, our starting point is we're going to assume no local changes in geopotential height, so we're only considering kinematics. That is, we're assuming a fluid parcel that is responding to an imposed geopotential height field. We're going to assume horizontal flow only on a constant pressure surface. We're going to assume no friction, so we're again neglecting near surface friction that could be causing slowing or adjustment of the flow. We're going to assume, for instance, that this flow is occurring at sufficiently high altitude that it's not subject to boundary layer friction that might be present in the near surface. And this will allow us to then define a Lagrangian parcel approach to natural coordinates. For those of you who don't remember the Lagrangian partial approach, you can go back to Chapter 1, lecture on material derivative, to learn more about Lagrangian parcels. Alright, let's now define our coordinate system then associated with natural coordinates. So what we're going to start with then is this notion that we can define a coordinate system which is somehow related to the direction that the fluid parcel itself is actually moving in. And so at every point we're going to define a unit vector or a vector of unit length which points in that direction of motion. In the case of fluid flow along lines of constant geopotential, we then have that these tangent vectors, which point in the direction of the fluid flow, are then also vectors which are tangent to lines of constant geopotential. A second vector is then defined, known as the normal direction, and this is always going to be to the left of the tangent vector at a 90-degree angle, and this denotes a direction which is normal to the direction of the wind flow. That is, it's always 90 degrees to the left of the wind flow. The normal basis vector then is connected with the tangent basis vector through the right-hand rule. This requires us to use another vector, which is the local vertical vector, denoted here k. That is going to be the vector that actually points out of the page. And n is then defined as k cross t, giving rise to a normal vector which is always oriented 90 degrees to the left of the flow. Recall from the rules of cross products that the normal vector then is always perpendicular to both vectors k and t. So the advantage of defining this natural coordinate system is it seems to be very tightly intertwined with the natural flow of individual fluid parcels. So we can assess, for instance, geopotential height on a pressure surface and estimate wind speed then using this local notion of coordinates. No matter which direction you're pointing in, the geopotential height gradient that defines the geostrophic wind locally is only going to be defined by the derivative in the normal direction of the flow. In general, it's difficult to measure wind, so using this normal direction plus, for instance, a finite difference relationship, it's going to be very easy then to estimate wind speed simply using the geopotential height field and this notion of a normal vector to the flow. Further, we're going to see that this natural coordinate system is very useful for both diagnostics and interpretation of why exactly fluid parcels behave the way that they do. In order to answer that question, though, we're going to actually need an equation that describes the underlying fluid motion in this natural coordinate system. Okay, so there's a few concepts that we need to touch on first before we can proceed with actually deriving that equation. One thing is this notion of the normal direction inducing an idea of curvature associated with the flow. So I want you to look at this diagram, and what you might notice is that as the fluid parcel moves around a curve, that is, as the tangent vector changes, as it follows along this line of constant geopotential, that the normal vector to the flow seems to be pointing off to a central point far in the distance. Actually, if we take these vectors and extend them further, you can imagine that they are pointing at an object far in the distance. So, in some sense, the fluid parcel is experiencing a centripetal acceleration due to this force in the normal direction. That is, if you think of the fluid parcel located here at the point of contact between the normal and tangent basis vectors, and you can imagine it tied to a string extending in the normal direction to some sort of hook or pulley, that as that fluid parcel goes around the curve, it's kind of analogous to the force that it would experience if it is, for instance, being swung around over your head or swung around a central pulley. So we can imagine then that the curvature on the flow then is going to be somehow connected with this idea of centripetal acceleration. So in order to actually quantify this idea, we're going to need to define a concept known as the radius of curvature, here denoted by capital R. And that's the idea that if the fluid flow locally was experiencing a centripetal acceleration due to the fact that it was tied to some central pulley and kind of being swung around because of its connection to that pulley, then the radius of the associated motion, that is, of a circle, for instance, imposed on the flow, that is tangent to the location of the fluid parcel, the radius of that swinging motion then is going to be known as this radius of curvature. And it's going to share the same curvature as the local flow. In fact, if we impose this circle on the local flow, what we'll find is that it's a much better approximation to the local behavior of the geopotential height contour than a straight line. It's kind of like the next order approximation of how exactly that geopotential height contour is changing with respect to space. Now, the velocity that a fluid parcel is actually experiencing in natural coordinates can be very easily written in terms of our underlying coordinate system. Specifically, we know that the velocity is always pointing in the direction of the tangent basis vector. However, the tangent basis vector is of unit magnitude, so it doesn't convey any information on the magnitude of the velocity. However, if we define a velocity magnitude, here denoted by capital V, we can then multiply that by the unit tangent vector, and that'll give us our fluid parcel velocity vector. So another way that you can write this is if you take the absolute value of both sides, or the magnitude of both sides. Actually, the tangent vector only has unit length associated with it, so this capital V velocity magnitude is simply the magnitude of the velocity vector. So the key simplifications that we introduce here is that the velocity is always in the direction of t, and we also know that the value of this velocity is always positive. Although the tangent vector itself can swing around and can point in different directions in space, the magnitude is always positive, always aligned with the tangent vector. So in order to understand how acceleration then works in natural coordinates, you simply need to remember that acceleration is the material derivative of the velocity vector, that is the change in velocity following a fluid parcel. If we then plug in the definition of the velocity in natural coordinates from the previous slide and apply chain rule to this expansion, what we observe is that the acceleration in natural coordinates becomes a two-termed acceleration. You have a first term here, which is associated with the local change in the velocity magnitude, but that acceleration is experienced in the direction of the tangent vector. And you have a second term, which is associated with a change in direction of the fluid parcel. So this kind of makes sense. Basically, you have a term which is acceleration in the direction of the flow. So that's not associated with the underlying curvature, that's just associated with local accelerations. And you have a change in direction. Now, the change in direction will be what is associated with the underlying curvature. So again, the first term here, change in speed, change in magnitude of velocity. Second term, change in direction of the flow. Okay, so how do we simplify this change in direction term? As much fun as it is to have a material derivative of a local tangent vector sitting around, we need to actually be able to write this in terms of quantities that we understand more intuitively. Specifically, how do we write this as a function of the local velocity magnitude and the local radius of curvature? So what we're going to do is then assume that the fluid parcel is moving along this circular trajectory. For small adjustments in the flow, this is a very good approximation to how the overall flow is behaving. And we're going to use circle geometry in order to derive an expression for the material derivative change then of the tangent vector. Let's assume that we have a fluid parcel here denoted by a blue box with initial tangent vector t1 that then adjusts its position to position on the top of this diagram, the second blue box then located with tangent vector t2. Because it's following along a circle, we then know exactly the location. We know that it has the same radius from the center of the circle at both position 1 and position 2. And over this distance, we're going to define the angle subtended by the motion as delta theta. So now let's take this vector t1 from the initial position, the initial tangent unit vector associated with the flow, and let's move it up to position 2 so that we can draw a triangle. Although it looks like it's not perfectly a right angle triangle, but we'll get into that in a bit more detail in a moment. We're going to define this change in the tangent vector then as this delta t term. So delta boldface t, this is again a vector, and it is the vector difference between t2 and t1, or in other words, we can write t2 is equal to t1 plus delta t. Okay, now let's just use some simple triangle geometry here. So we're going to define this angle alpha as the angle between the vector t1 and the vector delta t, and this vector, recall that by simple triangle geometry, we know also that the internal angle between t1 and t2 within this triangle is simply given by delta theta, again the angle subtended because of the fluid parcel motion. I leave it as an exercise to the viewer in order to understand that this is the case. Now, using the law of sines and the fact that the tangent vectors themselves are always of unit length, that is of length 1, we can use the fact that the sine of an angle divided by the length of the opposite side of the triangle is equal to a sine of any other angle within the triangle divided by its opposite length. We know that the two angles defined by alpha and the angle defined by pi minus alpha minus delta theta, that is the angle that appears at the connection point between delta t and t2 will have opposite lengths equal to 1, because in both cases the opposite angle or the opposite side of the triangle is defined by a tangent vector with unit length associated with it. So since all angles are less than 90 degrees, it turns out that the uniqueness of the sine function in this case can then be used in order to equate the arguments of the sine. So that is, we know that not only is the sines of these angles equal to one another via the law of sines, but actually the angles themselves also need to be equal to one another. So equating these two, we get alpha equals pi minus alpha minus delta theta, and solving for alpha, that is moving the alpha to the left-hand side, dividing through by 2, then gives alpha must equal pi by 2 minus delta theta over 2. So this angle alpha here, which looks like it's almost 90 degrees in the triangle, is actually a little less than 90 degrees. Recall pi by 2 radians is exactly equal to 90 degrees, and so the angle alpha must be a little bit less than 90 degrees, and that difference is actually given by delta theta over 2. However, for small displacements, and using the fact that the tangent vectors are of unit length to one another, we actually then have from this previous expression that the magnitude of the delta t has to be given approximately by the angle subtended by these vectors, and consequently that the actual vector itself is approximately given by the angle subtended times the normal vector defined at the initial position. That is, if we assume that the angle alpha is approximately 90 degrees, as is the case for very, very small values of delta theta, then we can conclude from this that the length of this tangent vector difference is going to be given by delta theta, and consequently that delta t is approximately equal to delta theta times n1, which is a unit vector in the normal direction at the initial position. All right, so we know that also over the distance, between point 1 and point 2, the distance traveled by the fluid parcel is going to be given by this quantity delta s, and that simply emerges from circle geometry, namely that if you have a distance in radians and a radius of the circle given by r, then that chunk of the circumference of the circle is going to have distance equal to r times the angle subtended between the two. And so rearranging this equation for delta theta, plugging it into the definition for delta t above, we then have that this change in the tangent vector is approximately given by the distance traveled by the fluid parcel between these 2 points divided by the radius of curvature and multiplied by the normal vector located at position 1. So this approximation holds sufficiently accurately that in the limit of very, very small fluid motion, so basically taking time to 0, we'll have that this approximation holds in that limit, and so we can apply calculus then in order to turn this into a derivative relationship. So dividing through our expression by time, here denoted by delta t without the boldface, we have also using the fact that distance divided by time is given by velocity. So if our velocity of our fluid parcel is given by velocity capital V, then the distance it travels divided by the time it takes must be given by that quantity V as well, and so we can plug in V in this expression. Then we have that the change in the tangent vector over time is approximately equal to V over R times N1, or in the limit as delta t goes to 0, we have that the material derivative of the tangent vector with respect to time is exactly given by the magnitude of the velocity of the fluid parcel divided by the radius of curvature times the local normal vector. Here we've dropped the 1 subscript on the normal vector because in the limit of infinitesimally small times, the normal vector at position 2 and the normal vector at position 1 will coincide with one another. And so it all basically depends on that normal at the initial time. Okay, so remember our goal was to quantify the acceleration. We wrote down our expression for the acceleration of the fluid parcel using the material derivative of the velocity vector. We wrote that out using 2 terms, one of which is the acceleration in the direction of the fluid flow, and another one which is associated with the curvature of the fluid flow, or the adjustment in the direction of the tangent vector. However, from our previous derivation, we now have that the material derivative of the tangent vector can be written more simply as v over r times the normal vector. So we plug that in and we get that the acceleration experienced by the fluid parcel is equal to a change in speed term that we discussed previously, plus v squared over r times the normal vector. Here, of course, we get the v squared because we get a v from the dt dt, and we get a v that it pops up in our original quantification of the acceleration from the chain rule. So what does this term represent? Some of you may be saying, aha, at this point, as this term does look somewhat familiar from basic physics. And in fact, it actually looks exactly like centripetal acceleration. So those of you who recall your basic physics knowledge, you'll remember that centripetal acceleration actually looks exactly like v squared over r. Just checking that the units of this are correct. We're looking for a term that's an acceleration. V squared has units of length squared divided by time squared. Divide that through by a radius of curvature, which has units of length, and you get a term that looks like length divided by time squared, and that is exactly an acceleration term. So these 2 terms that then pop out from the chain rule expansion of the acceleration in natural coordinates are then the change in speed following the flow and the centripetal acceleration due to curvature in the flow. So we have in natural coordinates then derived a term which represents the underlying curvature. Alright, so now that we have an equation for the change in the horizontal momentum in terms of tangential and normal vectors, we'd like to derive a momentum equation. So this momentum equation will then include the acceleration, Coriolis force, pressure gradient force, and in particular the acceleration term here will then incorporate the curvature associated with the flow. So Coriolis force, as usual, always acts normal to the velocity. Coriolis force then, actually very simply in natural coordinates, then must take the form F Coriolis equals negative Fk cross u. Recall u is simply given by magnitude of the velocity times the tangent vector. And so plugging that in, using the fact that n equals k cross t, then gives us an expression for the Coriolis force that looks like negative Fvn. So very simple form in natural coordinates. The pressure gradient force can be expanded as a gradient in both the tangent and the normal directions. So we're just going to take that gradient term then, and we're going to say, okay, we've got a gradient in the tangent direction, so that's just a directional derivative. For those of you more familiar with multivariable calculus, that's just a directional derivative in the t direction and a directional derivative in the n direction. And so basically, if you define a coordinate system S that points in, or a coordinate S that points in the t direction, then that's going to be simply given by di phi di s, and you're going to get a coordinate n in the normal direction that then induces a term for the gradient that looks like di phi di n, and so the combined pressure gradient force then is negative t times the derivative of the geopotential height field in the t direction plus n times the derivative of the geopotential height field in the normal direction. So nothing particularly exciting here, just notation. So take the vector form of the momentum equation, make all the substitutions, use the acceleration that we derived from this lecture, use pressure gradient force, use the Coriolis force, substitute everything in, and we get a nice expression here at the bottom that relates all of the terms that we've derived in natural coordinates to a single momentum equation. So a single equation that describes how the momentum then evolves within the flow. All right, so you'll notice that some of these terms have n's, some of these terms have t's. N's and t's are perpendicular to one another, so actually we can extract all the terms that have t's and all the terms that have n's, and those become two equations that actually must hold independent of one another. So in component form, we have a momentum equation along the flow direction, and that is that the acceleration or the change in magnitude of the velocity experienced by the fluid parcel has to be given by the change in geopotential in the s direction, or the change in geopotential tangent to the flow. So that is the only thing that can induce a change in the magnitude of the velocity of the fluid parcel is a pressure gradient in the direction of that fluid parcel's motion. And the second equation that then emerges is this equation that actually describes a force balance for the fluid parcel. That is, we must have a balance between centripetal acceleration experienced by the fluid parcel, Coriolis force, here given by Fv, and pressure gradient force, which is the derivative of the geopotential in the normal direction. However, we can simplify this actually further, and by noting that the equation we've just derived in the flow direction simplifies pretty dramatically when we require that there be no change to the geopotential height contours. Because we know that the fluid parcels are moving along lines of constant geopotential, that must then imply that the change in geopotential in the direction of the fluid motion must be zero. And so the right-hand side of this momentum equation in the flow direction must be zero, and consequently we must have that the left-hand side also be zero for the equality to hold. So this equation simply reduces to 0 equals 0 then. And so the momentum equation, the vector momentum equation, describing horizontal motion, then reduces to a single balanced law, which describes how forces in the normal direction must balance one another. So only one diagnostic equation then emerges from natural coordinates to describe the velocity of the fluid parcel. So what does this equation look like again? First term, centripetal acceleration of the fluid flow associated with horizontal curvature of lines of constant geopotential. A Coriolis force term. And on the right-hand side, a pressure gradient force term associated with changes in pressure gradient perpendicular to lines of constant geopotential. So the question is then, how does this generalize the geostrophic approximation? In the case of the geostrophic approximation, it actually turns out that we can drop one of these terms. And that term is the centripetal acceleration term here on the left-hand side. The geostrophic approximation assumes no underlying curvature within the flow, so this term is neglected, and so we simply reduce to an expression containing the last two terms of this equation. You might notice then that is simply corresponding to a balance between Coriolis force and pressure gradient force.